Okay, so good morning. This is Mr. Martin 2020, August, and we're going to look at the big ideas in physics. We're going to look at the principles today, just the principles that are behind everything that we learned. So we have here a man standing surrounded by the elements of nature. Of course, the elements of nature are related to the fields in physics. 99.9% of the universe is space, and that's what we study in astrophysics, in quantum physics. The space in between the atoms, the space inside the atoms, the space inside the nucleus of the atoms, and the big space where waves, electromagnetic waves travel, electromagnetism, all that has to do with space around us. Then fire, heat, the study of heat as a field in physics, thermodynamics and all that, air, gases, the study of gases, hydraulics for water, and mechanics for earth. These are the 5 fields in physics, and we're going to look at the principles. What is a principle? A principle is a statement that we must accept as true in order to start learning physics. You can't, in the same way that you cannot build up the math without starting from axioms, you cannot build up physics without accepting certain principles. So let's see what are the principles in the different fields of physics. We're going to go into space, electromagnetism, universe. So what are the true statements there? We link there. Akasha is the word used by the ancient Vedic science to describe this mysterious space. So let's look into the statements that are true or that has been discovered. To be honest, these statements weren't posed from the beginning. They were discovered with deep research and experimentation. So these are the principles: uncertainty, relativity, superposition, the cosmological principle. We're going to go into each one of them. We're not going to go into too much detail, but the first principle was stated by Werner Heisenberg, a very important principle. You cannot know at the same time the position and the momentum of any particle. For example, if you want to know the position of the momentum of an electron at the same time, you can only know to a certain precision one or the other. There is a very good video here explaining the principle of uncertainty. I don't want to go too much into the explanation, but just there is a limit to what we can know or measure in science. That is a conclusion of modern science that changed the way we understood physics as a deterministic science, no more deterministic, and gave birth to quantum mechanics, the new physics that we will study in the IB this year. So we leave it there. There is an uncertainty to momentum and position, or also to energy and time. The principle of uncertainty is responsible for, and I wouldn't say responsible, is the reason why we are able to understand virtual particles. They exist for such a small period of time that the ranges of energy could be quite big, so they can borrow energy to pop out into existence. This is what explains how matter pops out into existence from nothing. Matter and antimatter. So we'll talk about this later on. There is a video for the principle of uncertainty. We're not going to go there. Second principle, the principle of relativity. The laws of physics are true for all observers. That means the laws of physics are universal and eternal, independent of where you are standing. Galileo Galilei stated this principle, and then Albert Einstein extended it to all systems, not just inertial systems, that move with uniform motion relative to each other, but to all systems, accelerated systems, non-inertial systems of reference. We should all be able to explain the phenomena using the same laws. So the principle of relativity is not does not mean that truth is relative. I have my truth, you have your truth, I respect you. No, no, no. It means exactly the opposite. It means there is only one truth. And those equations should be the same to explain the same phenomena, independent of the observer. So there is a video there explaining it. I'm going to skip it. Principle of superposition. When two or more waves overlap, the overall displacement is the vector sum of each displacement. That means waves do not collide with each other. They overlap. They produce a total dispersion or vibration in the media where they are traveling. That is the vector sum of each displacement. In other words, if I speak and somebody else speaks, you hear both. There is interference, but that means that waves pass through waves. Same with light. A very important principle in waves, superposition. So we need to learn how to state these principles. So the cosmological principle is a principle that states that the universe is homogeneous and isotropic. We're going to see what that means now. It is a very important principle for astrophysics. So it's a statement that we accept as true again. It's a principle. We do not question this. Now, if we could find evidence that challenges a principle, that principle would not be a principle, right? So let's listen to this explanation on the cosmological principle.
When we look out into the universe far enough, we see on average the same distribution of galaxies in all directions. In other words, there is no preferred direction in space. It's isotropic. But being isotropic for us doesn't necessarily mean it is isotropic for viewers in far-off locations. It is possible to imagine galaxy configurations where things look the same in all directions from one point of view and not from another. But this is unlikely. Our assumption is that all observers will see the same isotropic distribution of galaxies. In other words, there is no preferred location in the universe. It's homogeneous.
Homogeneous.
Galaxy densities are the same everywhere, as long as we are viewing large enough distances and volumes. This is the...
Okay, so I pause it there. So as long as we are looking at large enough distances and volumes of the universe, this principle stands true. It is homogeneous, that means the same density of galaxies in all directions, and isotropic, there is no preferred direction. Let's move on. Next principle. The equivalence principle, another principle stated by Albert Einstein. The equivalence principle states that gravitational and inertial masses are equivalent. That means if you are standing in a gravitational field, or if you are standing in a lift that is accelerating upwards, there is no difference. One is a gravitational field and the other one is an inertial mass moving upwards. So he established a principle by which, this is the consequence of this principle is the fact that light bends when it passes through gravitational fields. This is a very interesting consequence, and we're going to look at this when we study astrophysics later on this year. But again, the principle of equivalence, I am going to skip the video, maybe watch it together. Another principle stated by Albert Einstein, the speed of light is a universal constant regardless of the motion of the source of the observer. It doesn't matter if the observer or the emission, the source of emission of light is moving, the speed of light does not carry with it the velocity of the source. Like, for example, if a plane drops an apple, the apple carries the velocity of the plane, so it produces a parabolic motion. If you throw a beam of light forward or backwards from a plane in both directions, Light travels at the same speed. Very important principle. We're going to watch this later on. Action and reaction. We saw this law, which is, you know, the difference between a law and a principle is that a law is a mathematical equation. So for every action there is an opposite and equal, or equal and opposite reaction. This is known as Newton's third law. You can express it as an equation. F12 equals minus F21, right? The force of the moon on the earth is equal to the force of the earth on the moon. One produces the tides, and the other one produces the fact that the moon cannot turn the face away from us. It's always facing in one direction. So those are the pairs of forces. Another way of stating this principle is saying that forces in nature always appear in pairs. It is impossible to have a single force happening in the universe. So we skip the explanation, and then comes the theories. So these are the principles in astrophysics. We're not going to go into theories. We're going to go back to the original slide here. Again, we're going to go into heat. Let's see in heat, what principles and statements do we study for the IB diploma in heat? Energy cannot be created or destroyed. Energy can only be transformed. This is a very important principle. The energy inside a closed system is conserved. We believe in that. And since we believe in that, we're finding it very hard to understand where is the dark energy that is creating an increasing expansion of the universe coming from. We don't know where that energy is coming from. 75% of the universe is dark energy that violates the principle of conservation of energy. The universe is getting energy from some mysterious space that we can't see, we can't yet understand. Same thing for the pop out of matter and antimatter. No? It needs to explain a violation of energy. So that's quantum physics, violation of the principle of conservation of energy. What else? Heat and thermodynamics. Is there anything else beyond the IB? No, nothing else. Okay. Let's go back to the principles in air, gases. What do we have there? What statements for gases that we study in the IB? Nothing really that I can think of. Maybe it would be nice to find out if there is any principle in gases. What about the hydraulic? For the IB, yeah, Archimedes' principle, you know, the buoyancy. It states something that is very intuitive. When you put your body inside a pool, there is a force pushing upwards that is equal to the volume, the weight of the water that your volume is displacing away is wanting to go back into that position. So that creates an upthrust. Apparently Archimedes discovered this and jumped out of a bathtub naked. So there is a video there explaining it. And any other principle related to water? Yeah. Bernoulli principle is beyond the IB. It is the conservation of energy, but applied to liquids. So we're not going to go into that with detail, but you've got the videos there. So those are the principles. And mechanics, we saw a few, right? Mechanics, conservation of, let's see, mass. This is also applied in chemistry, right? It's a law. Sometimes the principles derive in very simple laws like inertia. Yeah? The law of conservation of mass. On one side of the equation, there's always the same amount of mass as on the other side of the equation. Mass cannot be created or destroyed. Inertia, it's also a principle, but it's a law. This is a very interesting video. A body will not change its state of motion unless an unbalanced force acts on it. That's a principle. The law is F equals ma. Yeah? So a principle becomes a law when we find the equations. And the principle of conservation of momentum that applies to linear momentum, which is very simple, similar to the principle of conservation of momentum and the principle of inertia, I would say are the same idea. Yeah? So if no force acts on the system, the total momentum remains constant. There is a T missing there. And the same thing with the angular momentum. When rigid bodies spin, if there is no external torque acting on it, the angular momentum must be conserved. So if you change for example, a dancer that brings the hands closer will spin faster because the moment of inertia decreases, so the angular frequency increases. Okay, this is rigid body. This is an option in the IB that I don't think we are going to study this year. So this is an interactive web page where you can look at principles, theories, laws, concepts that we study for IB physics. Just play with it. It's a video game.